Question for you.
Thank you, Alexis. Go ahead.
A car with a mass m is rounding a circular horizontal curve with a radius r.
All
The
right.
coefficient of static friction for the tires on the road is normal static.
Okay. So what I didn't see enough, like I know you're getting used to this thing, and it's not like easy to visualize these things, but I would recommend like kind of a back view. So like someone following, like say it's my car and I'm driving home. Where I live, there's lots of turns and stuff in the mountains. So there's like my bumper, there's like my rear window. I know it's not the greatest picture, but I'm trying to draw from behind. Do you guys follow me?
Yeah.
And do you want it, the way I've drawn it, maybe it's a right turn because I have more space on the right side. Okay? So I'll write car turning right, because you can't tell. So car turning right. Can you all yell out the direction of the acceleration then?
Right.
Okay, stop. No noise for a sec. If you're having trouble figuring it out, maybe a bird's eye view. I'll do a bird's eye view over here.
No, I just screamed something random out.
Okay, so this is bird's eye. And, you know, the turn might be like this. Yeah? There's the turn I'm going around. And my car is here. That's bird's eye at the same moment in time. This is behind view, right? Behind viewpoint. Okay, so can you all see now that the acceleration is which way? Okay, I'll draw it here, and I'll draw it right here. And that's towards center of circle, right? Towards center of circular path. So if you get through enough of the key ideas, you're going to have success. That's the first big one, is correctly identifying the direction of your acceleration, right? So what are the forces acting, please? All right, and the reason that behind view perspective is so good is because it really makes my force diagram simple. So there's weight. You said weight. You said normal. Force what? From what? Okay, I'm not sure I understand what you're talking about. Forces are always due to objects, right? Exerting force on your system. What is exerting force on the system here? I think what you're talking about is people use radial to describe a direction. They just mean centripetal. They just mean towards center. And there's no magical force towards center. There's just regular forces that we're already familiar with acting on objects. And we're going to use Newton's second law in a direction towards center. That's all we're doing here. It's the same thing we've been doing. It's just in 2 dimensions now. Okay? And are there any other forces acting here? There has to be. Friction. Which way would your static friction have to be to provide net force towards the center?
Which way would what?
Which way would your static friction need to be such that our forces add up to a net force towards center? We need a net force towards center for this problem to work out. Yeah. Think about it. If your static friction is to the right, now when I add my forces, I got normal, I got static friction. Can I call static friction mu normal? It's on your reference sheet. You shouldn't think you got to memorize. You don't. So mu normal, I'm replacing static friction with mu normal. And then I got mg for weight. Is everybody cool there? Which way is our net force now? Okay, if I had made static friction to the left, it would have been wrong because my net force would have wound up being to the left. See, I think what's bothering you guys is when you turn a car to the right, it feels like there's a force to the left. What's really happening, like take that bird's eye picture up there. if I were to fall out the car, right? If there were nothing holding me in the car, which direction would I actually move while the car turns away from me? So I'd go straight, right? I would just keep going in a straight line. There is no force pulling me out of the car if the door is open and I fall out the door. I fall out the car. You guys follow what I'm saying?
Yeah.
So if there's no doors on the car, I have no seatbelt, and the seats are slippery. Car turns right under me, and I go straight. But it feels like I got pulled out of the car. I actually didn't. I actually went straight. What's really going on is there's a net force that keeps you in the circle. Or there's no net force and you go in a straight line. You see the difference? So, again, what's really happening here is if you go in a straight line with a constant velocity, there's no acceleration, there's no net force. That's what happens when you fall out of the car. If that happens, I don't want it to happen. But if you were to fall out, even though it feels like you're pulled out, you weren't pulled by anything. You went straight. You'd have to do the bird's eye view to understand that situation better, right? But now from the behind the view of the car, the force which holds your car in that circle is the road pushing on the tires. Think about it. Wouldn't I follow a straight line with my car if the road were icy and there's no friction? The car would just go in a straight line. It's the same idea. What's keeping the car in the circle?
Friction.
Yeah, and this would be static friction because I'm not sliding. Does that help a little bit? That's a tough idea. I'm glad you asked. Yeah.
Also, the way I figured out that the net force was going to the right was because in your circular diagram you have acceleration going to the right, and net force is to be the same direction as.
I really love that you said that. That's why I want everyone to draw the direction of acceleration next to their diagram every time, forever. I think it'll help you. Because when you do that, you'll know that your net force has to be in agreement. Your MA vector has to point in the direction of A, right? Go ahead.
And A has to always be in the direction of the center, right?
If you're moving in a circle with a constant speed, we know our acceleration is towards the center. Totally correct. But only if you know you're going in a circle with a constant speed, right? And that's why I'm allowed to put v squared over r in place of acceleration, because only when you're going in a circle with a constant speed can you say that your centripetal acceleration is a magnitude of v squared over r. And that's looks like it's 1, 2, 3, 4, 5. That's the 6th mathematical model on your reference sheet. You guys cool?
Okay.
All right. So we're pretty much done with the physics here. Can you tell me what normal equals?
Normal equals gravity, or weight, mg.
Yeah, mg. Good. Now, can you tell me what
Mu normal.
yeah, what's mu normal going to equal?
Net force, but that's like, I can't force.
mv squared over r? Is that cool? And I think here we're trying to find the maximum speed that the car can do the turn, right? So solve this equation for what? We're trying to find the maximum speed. The reason it's a maximum speed is this static friction is really a maximum static friction that surface is capable of. So any speed faster than this and there won't be enough friction. Does that make sense? So this is a maximum speed. You get v squared equals what? I need your help, people. Okay, r mu static n over m. You can do more now, people. What's normal equal to? So you see the substitution you can do? So over here you get v squared equals r mu static.
And just G.
Oh, you can remove the M, so it'll be just.
Isn't that cool? What did that teach us right now, right away? How does the mass affect this maximum speed? Good. That's kind of cool, right? Especially for an engineer. And think about it. If you were designing a road, a highway, like if you were getting paid those folks probably get paid like $500 a day. It's good money, and they're using physics to come up with those signs on the road that tell you how fast you can go. Well, guess how they do it? Is it possible to look at what size radius would fit that curve? Is that possible? They just go measure it. They figure out the radius of the circle that would fit that curve, and then they use this equation here, and they say, well, first curve they do has one radius. They get a speed v. Let's say your radius goes up by 4. You guys with me? You got a curve with 4 times larger radius. How much faster could you drive on that curve?
2 times.
You would only be able to go 2 times faster. Why is that? Yeah, v squared is proportional to r, or you could say v is proportional to square root of r. So if r goes up 4 times, the speed goes up by 2. Or I could say, hey, now I'm getting to a real small curve where the curve is sharp. Now, let's say the radius is 1/16. 1/16 the prior curve. How much slower do you have to go?
What was 160?
So, if the curve's radius is 1/16 the size of the prior curve, how much slower are you going to need to go? Does that make sense? You got to go 1/4 the speed to make it through that curve when the radius is, what would we say, 16 times smaller? Or 1/16 times the prior radius. Are you getting the game I'm playing with the proportional reasoning? You should practice that. And like mu static. What if your mu static? What if it was raining and your static friction were 1/9 the prior day? You guys follow what I'm saying? You got 1/9 the mu. How much slower do you have to drive? Notice that v is proportional to square root of mu static. Or you could say v squared is proportional to mu static. How much slower do you have to go if the mu is 1/9? Yeah. You have to cut your speed into 1/3. Now, most people, when it rains, they don't cut their speed into 1/3. That's why there's all kinds of accidents. Make sense? And reality is, you probably got 1/100th the mu when it rains because you have water mixing with oil. You have almost 0 friction. So if you had 1/100th the mu, how much less speed do you need then to not slide out 1/10? So you really have to slow down when it rains, and again, people just don't even slow down, right?
How would you have oil mixed with water? I'm just very curious.
Because there's oil on the road from cars like mine that drip.
Oh.
I'm just kidding. I hope my car doesn't drip. But you get what I'm saying, right? There's a lot of oil on the road. I get to surf in it when it rains. It's beautiful. Cool. All right, I'm going to stop the video.